Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to talk about a different example of an isometry. We're going to talk about something called a translation. And I want you to think of a translation as a transformation of the plane that takes an object and slides it. So that's the kind of transformation we'll be talking about in this video. So the idea that we want to develop or make sense out of is this idea of sliding using a vector. So a vector is very naturally the right kind of object to think about in order to make sense of a translation. Now there's a little bit of bad news here, which is that we have not defined vectors in this class. As a matter of fact, there is an equivalence, fundamental equivalence between defining vectors geometrically and defining translations. So once we've defined one, we can think of the other one as just falling out of it as a consequence. Okay, so we're going to take the point of view that we have not defined vectors yet, and instead are now going to define translations. Okay, so we don't, like I said, we don't have this notion of vectors in our development of Euclidean geometry, but what we can do instead is one of two definitions. So there's merit to either perspective, and we'll see that one of them is more convenient than the other, at least from my point of view. The more convenient one is going to be very similar to what we did with rotations in the last video, where we are going to compose some reflections in order to define the translation. Okay, so for this topic especially, we really are assuming that we're working in Euclidean geometry. One of the reasons for that is that making sense out of vector addition in hyperbolic geometry is kind of difficult and a problem, and it doesn't really work the way you want it to in hyperbolic geometry. So we're just really focused now on Euclidean geometry. And that's been pretty much true for this whole module on transformations. Many of the things we've said work in hyperbolic geometry, but let's just go ahead and assume we're working in Euclidean. So here's a picture of a translation. Right, I have my 2 points A, B, and we're secretly thinking of them as defining a vector for us. Right, we're thinking of going from A to B. And I have here a triangle, UVW. And then if I translate it, I get this new triangle, U prime, V prime, W prime. Okay, so the first definition is very geometric. So the idea is, if I want to translate by a vector AB, what I'm doing is I'm moving the vector AB to have its tail at P. And the way you learned how to do that is by the so-called parallelogram rule. Right, so if I have a line here, AB, and I have a point, let's say I have a point here, P, I have a point there, P, then what I want to do is I want to construct a line incident to P that's parallel to AB, right? And this one exists and is unique by the Euclidean parallel postulate. And then I want to put a point over here, let's say, it'll be about there. This is the point P prime, so that now my dotted lines here should also be parallel to each other. And I do that kind of freehand, so it might not be accurate, but that's the basic idea. Right? So if P is not incident to the line AB, we want to define P prime to be the unique point so that my quadrilateral A, B, P prime, P should be a parallelogram. This is very good in some ways. Right? The very good thing about it is that it really feels the Euclidean geometry. Right? We use that parallel postulate. It's a very geometric construction. The bad thing about it is it does not tell us exactly what to do when P is incident to the line AB. And the downside to that is we now need to break down into cases depending on, and if let's say P is here, then I need to somehow explain that P prime is moving to the right and not to the left. In our case when P was not on the line, this parallelogram rule forced us which direction to move, right? It forces us to move to the right. Whereas if we're on the line, to talk about moving to the right, we need to start using the betweenness relations. And that gets very cumbersome because we need to look at cases about whether P and B are on the same side of A or if they're on opposite sides of A. So you end up with a bunch of cases of what to do. It's not too bad, but it is somewhat cumbersome. I think there are like 3 cases you end up writing down. So now that leads us to our second and perhaps slightly more convenient method, which is a method of reflections. So for this, we're going to start by taking L to be the perpendicular bisector of my segment AB, and L prime will be the line perpendicular to AB passing through B. And the steps are, we first reflect through L, and then we reflect through L prime. And then I'm going to have you check also on the homework that this matches definition 1, at least if we start with a point P that is not incident to the line AB. Let's draw a little picture of what this means. Okay, so here I have my line AB. I have the perpendicular bisector L. Right, so the blue line L is the perpendicular bisector of the segment AB. And L prime is the line perpendicular to AB passing through B. So what we do is we first reflect through L, and then we reflect through L prime. So for instance, if I start here with a point P, I reflect it through L. That gives me a point, let me call it Q. And then now we reflect Q through L prime. And we get something like so. Right, so we do this in 2 steps. And the interesting thing is that gives us the translation that we claim that we need from definition 1. So that's something you'll be checking on the homework. And that's it for translations. Thank you for watching. Take a look at the homework problems. I think if you wrestle with this question here on the homework, it'll help you understand this perspective on reflections and how we can rewrite transformations, or I should say isometries, in terms of reflections. And I'll see you on the next one. Happy mathing.